Today I will discuss vector space. The definition of vector space V whose elements are called vectors involves an arbitrary field K whose elements are called scalars. So the following notation will be used. So we will use V as the vector space and small UVW as a vectors in the vector space V, capital K as a field and small ABC or K as a scalars in this field K. Let's see what is vector space. So to define vector space, we have to take set, non-empty set, and a field. So we take a non-empty set with two operations. So two operations is vectors addition. Vector addition means for any two vectors UV belongs to V, the sum U plus V also will be in the vector V. That is vector in the set. And scalar multiplication. If we take a vector from element from V and scalars from K, that is field, then the product will be in V. So then this V is called a vector space over the field K if the following axioms hold for any vectors UVW. So what are the axioms? There are 8 axioms in two part. First 4 and with respect to the addition, and second part with respect to the multiplication, vector multiplication with scalars. So in the first axioms, we see that U plus V plus W equal to U plus V plus W. That is, it's called associative property. Associative property. Okay. So for any three element U, V, W, this associative property hold. And second, there exists a vector in V denoted by 0, which is called 0 vector, such that for any U, this property hold, that is U plus 0. So if you add this 0 with any element of V, we get the same element U. And the third one, for each U belongs to V, there is a element or vector in V denoted by minus U, that is called negative of U, or this is called inverse, additive inverse. Okay, here 0 is called additive identity element, and this minus U is called additive inverse of U. So for each U, if there exists additive inverse of U in V, that is called minus U, such that U plus minus U plus U equal to 0, that is additive identity element. And the fourth one is commutative property, U plus V equal to V plus U for any two vectors U, V belongs to V. So these four property together imply that V is a commutative group with respect to addition, commutative group. And the last four one, that is scalar multiplication with vectors. So K into U plus V, that is U, V belongs to V and K is a scalar, then we get KU plus KV for any scalar K belongs to K. And if we take two scalars from capital K, that is A and B, then A plus B into U equal to AU plus BU for any two scalars AB belongs to K, and here U is the vector that is belongs to V, and AB, that is for any two scalars AB into U can be written as A into BU for any scalars this, and the one is the unit scalar in K, then 1U equal to U. So if these four property satisfied, then we call V is a vector space. So here is a theorem. Let V be a vector space over a field K. So as V is a vector space and K is a field, 0 is a scalar contained in K and 0 as a vector contained in vector space V. Then if we multiply these scalars with any non-zero vector, then we will get 0 vector, that is this 0 element from K and any vector from U, then we get 0, that is 0 into U equal to 0. And similarly, if we take non-zero scalars but 0 vector, then we get K0, K into 0 equal to 0. And If we get u into k, that is ku, k is a scalar and u is a vector equal to 0, then this will imply either equal to 0 or k equal to 0. So vector will be 0 or the scalar will be 0. If in this equation it is given that u is a non-zero vector, okay, u is a non-zero vector, then from this we conclude that k is a 0. So 0 scalar. And for any k and u, so if we find minus k into u, so it can be written as k into minus u, which will provide us minus k into. Okay, so now we discuss some examples of vector space. So first one is kn. Kn is a vector space. So as k is the arbitrary field, then kn is frequently used to denote the set of all n tuples of elements in k. So kn is look like a1 dot dot an. So where ai belongs to k. This is the set of all n tuples of elements in k. So the vector addition in this case look like this. So n tuple summation n tuple, so it will sum a1 b1 in the first position, and similar way, and scalar multiply k into this, so k will be multiplied with each and every element in n tuple, and here zero element will be the zero vector, the zero n tuple of zeros, and negative will be this minus, this will be minus a1 minus this. So therefore this kn will be vector space. So kn can be compared with rn. So these are similar. And after that pn. So this polynomial space pt denote the set of all polynomials of the form pt equal to a0 plus a1t plus a2t square plus dot dot as ts, where s is the degree of the polynomial, where s is not defined here. It can be less than equal to n or greater equal to n. So this will be vector space. And the polynomial space pnt, here the degree of polynomial is defined, that is n any polynomial in this set. This is a set of polynomials pt over a field k, where the degree of pt is less or equal to n, that is degree of pt will be less or equal to n. So if we take any pt in this field, this will look like this asts, where s less or equal to n, and therefore from this we see that this will be vector space. Similarly matrix space mn, so this is a set of all matrix with order m cross n in with entries in a field k. So this will be set of all matrices whose order m cross n and whose elements are taken from this field k. So this will be a vector space. And now we'll discuss field and subfield. So if E is a field and K is a subfield of E, then E can be considered as vector space over the field K. Okay, with this vector addition and multiplication. And now we discuss linear combination or spanning set. So linear combination, let a vector space V be a vector space over a field K, then a vector U in V. So V belongs to V, that is small a vector V in V is a linear combination of vectors u1 u2 dot dot um in V if there exist m scalars, that is a1 a2 dot dot am in K, such that V can be written as a1 u1 plus a2 u2 dot 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 plus dot dot am um. Okay, so V is a vector in V is said to be linear combination of vectors u1 u2 um if there exist scalars a1 a2 am, such that V can be written as v1 equal to a1 u1 plus dot 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 am um. So this can be written as summation ai ui I equal to 1 to m. So in other way you can define linear combination. V is a linear combination of u1 u2 um if there exists a solution to the vector equation. So directly if you can find the solution of this vector equation where x1 x2 xm are unknowns, then we said that V is a linear combination of U1, U2, Um. If there exists no solution x1, x2 dot dot xm, so this will be not a linear combination of U1, U2, Um. So let us take one example. Suppose we want to express this vector V in R3 as a linear combination of these three vectors U1, U2, U3, this. So this V equal to, we write V equal to x into this U1 plus y into U2 plus z into U3. So we have to find x, value of x, y, z, so that we can write this vector as a linear combination of these three. So from this we get a system of three linear equations. So by applying Gauss elimination method, you can find the solution of this equation. If there exists a solution for this system of linear equations, then we say this vector V can be written as a linear combination of these three vectors U1, U2, U3. So clearly if we apply Gauss elimination method, so first you eliminate x term from these two equation, then we get new system this, and from this last last equation you have to eliminate this y term, then we get this equation, and from this you simply can find the solution, that is x equal to 2, y equal to -4 and z equal to 3. So V can be written as 2 into x equal to 2 into u1 minus y equal to -4, that is -4 into u2 and plus 3 into u. So we can find x, y, z from this system. So we can say now that V can be expressed as a linear combination of this. This is also a example. Suppose we want to express this polynomial V as a linear combination of the polynomial P1, P2 and P3. So simply we write this V equal to, this is V equal to x into P1, y into P2, z into P3, and then expand the right hand side. So collect the coefficient of t square, coefficient of t and coefficient of t to the power 0, that is constant term. So from this we get, this will be 3, this will be plus 5 and this will be minus 5. So by solving this we get xyz. So from this applying operations you get this, and from this you get this. So from this you can find xyz. So then ultimately we get this result. So B can be written as 3 into P1, 1 into P2 minus 2 into this. So B is a linear combination of P1, P2, P3. Spanning set. Let V be a vector space over a field K. Then vectors U1, U2 dot dot Um in vector are said to be span V or to form a spanning set of V if every V in V is a linear combination of the vectors U1, U2, Un. That is, if there exist scalars A1, A2 dot dot M in K such that V equal to this. So vectors U1, U2, Um in V are said to span V or to form a spanning set of V if every V can be written as this. So we claim that the following vectors, that is E1, E2, E3 is a spanning set of R3. That is, every vector in R3 can be written as a linear combination of these three. So these vectors E1, E2, E3, this set will be the spanning set of R3. That is span R3. So this is called span V, means each span V means set of vectors. With the help of this vector, if you can express each and every element of V as a linear combination of these vectors, then we say this set is span V. So we'll discuss example later, and subspace we will discuss in the next video. So if you like it, please subscribe my channel and share with your friends. It will help you.